We're going to be talking about forces and free body diagrams. But before we get started, I want you to just think about it for a second. Pause this video, go ahead, pause it. Think about what exactly is a force. All right, I'm assuming you had enough time to pause the video and think about it. So a force is any sort of push or pull on an object. So let's give a quick little example right here. We got this nice box. We got this guy right here. We're going to call him Phred. He's got some really long arms. He's taking this box and he's pushing it around. His friend, Paul, over here, he's also very happy because they're both learning about physics today. He's like, hey, Phred, it looks like you're having a little bit of trouble with the box. I'm going to go ahead and pull that box on it. And they start talking. They're like, what exactly are we doing? What are we doing to this box? We're exerting forces on it. So it's very important to note that we look at forces from the perspective of the object experiencing the forces. In this case, the box is experiencing the forces. So instead of saying something like Phred pushed the box and Paul pulled the box, we would say something like the box experienced a push from Phred and a pulling force from Paul. Now, the last thing we need to talk about right away is how do we measure the units of force? So force is going to be measured in units that are called kilograms times meters per second squared, which you can also call, more commonly they're called actually, newtons, named after my guy, Sir Isaac Newton, the OG of physics. Now, in order to talk more about forces, instead of just saying something's pulling an object or pushing an object, we break it down into two main types of categories. We have contact forces, we have field forces. We'll start with the contact forces. So contact forces, as the name implies, it just has to do with a force that is being exerted on an object due to contact with that object. So some examples would be the force of friction, which I'm just going to write with the variable F sub F. The F right here, there should actually be an arrow above it for vector, but for the sake of space and time, I'm going to leave that vector off sometimes. The F stands for the force. The subscript right here, the small f, stands for friction. So another example of a contact force would be the applied force. Notice we put the big capital F still for force, but we have a subscript A for the applied force. An applied force is just going to be any sort of force that is, you guessed it, applied by some sort of person or animate object typically. Another type of force that we have is the force of tension. This one, you may be familiar with the term tension. Ooh, that's a terrible N. I apologize for that. It is tension, though. You may be familiar with the term tension. Typically, you think about the tension of a string or a rope. In physics, it's very similar. We're talking about a force exerted by a rope or any sort of pulling of a rope or string on an object. And the last contact force we're going to talk about for now is the normal force. So the normal force is a little challenging for students sometimes. Just think about it like this. The normal force is a force that is exerted by a surface on the object in contact with the surface. So if you have a book that's resting on top of a table, I'll even draw it. Here's a nice little table. My book's sitting on top. It's more of a box than anything. This table is also about to collapse, but that's okay. We'll give it a little bit more support. The book is applying a force on the table. It's because obviously gravity is pulling it down. However, the normal force of the table is exerting an upward force on the book, which is what stops it from falling through the table. It seems like it's a little bit of common sense, but it is very important to understand that the table does exert a force on the book. We call that the normal force. Now, there are other types of contact forces, such as the spring force and even air resistance, which I know we said we're not going to talk about too much, but it is important to know that that is a contact force. Spring force will come a lot more frequent later in the year when we start talking about the spring constant and Hooke's law and all that stuff. But for now, just focus on these 4 contact forces right here. We'll introduce more as we get more experience with drawing free body diagrams and understanding what forces are. Now, the other type of force we have is a field force. So a field force is something that acts on an object from a distance. The easiest one to think of is gravity. So gravity is going to be given the variable Fg. You'll also see this written as weight sometimes. So the force of gravity that's exerted on an object technically is the weight of the object. We'll go about how to calculate that later on, but it is also measured in newtons, just like all of the forces on the left over here. Another example of a field force would be the electrostatic force, or just the electric force, we'll call it for now. Electric force. And another one that we actually don't talk about in AP Physics 1, if you go on to take AP Physics 2, you will talk about it, is magnetic force. So field forces are a little bit easier because generally it's going to be gravity or the electric force. And if it's none of those two, all the other forces that are acting on an object at any given point will be from your contact forces over here. So keeping track of all these forces and visualizing them can be very challenging. There's an easy way to do it. It's with a technique called free body diagrams. So free body diagrams, I'll go through a couple of examples in just a minute, but a free body diagram is just a really nice way of organizing all of the forces that are being exerted on an object at any given time. Typically what you'll do is you'll represent your object as just a box or a dot like this. You might want to draw on the situation around it too. If it's an object sitting on the floor, you can draw the floor underneath it. If it's an object that is hanging from the ceiling, you can connect it to the ceiling with a string like so. The more creative you get with your pictures, the more you can really visualize the situation and the better your free body diagram is going to be. Now, I understand my picture drawing skills are absolutely atrocious, so hopefully your pictures will be a little bit better than mine, but you'll be able to get the gist of things as we go through this video. Now we're going to go through a couple of example problems, and what I want you to do is I want you to try them on your own. I'll introduce the first one to you, but the last three examples I want you to try creating a free body diagram on your own. Because one of my favorite quotes from Confucius, he said, "I hear and I forget, I see and I remember, I do and I understand." So the more you're actively participating in these videos, the more you're going to understand it and the more better off you're going to be when we get into class doing the much more challenging parts, the labs and the practice problems. All right, so let's take a look at example number one. A student pushes a box across a flat surface with considerable friction at a constant speed. Now, both of these underlined portions are going to be very important to pay attention to as we move on. The constant speed we'll talk a little bit more about when we get into Newton's second law, but essentially what that means is that all the forces acting on this box are balanced. In other words, the object is in equilibrium. Technically, it's kinetic equilibrium. We'll talk about the difference between kinetic and static equilibrium later on. But just remember, constant speed tells you the forces are balanced. The object is in equilibrium. So the first thing you want to do is go ahead and draw a picture. So we got this nice little box right here. Let's bring Phred back. He'll be our nice little physics assistant. Phred is spelled, just so you know, P-H-R-E-D, to make it a little bit more like physics. So Phred, he's going to push his box with one arm this time. He's feeling really strong today. So Phred is pushing this box across the floor. Floor is right here. Phred is somehow beneath the floor. Maybe there's a little divot right here that Phred's sitting in so he can get a little bit more ground behind him. I don't know what the situation is, but either way, Phred's pushing this box across a flat surface with considerable friction at a constant speed. So now we know Phred is pushing the object in this direction. This is not my free body diagram. I'm just saying that the velocity vector is in this direction and Phred is applying a force to the right. So there's a couple things you want to understand there. First of all, this velocity vector, this is not a force. There is no force of motion. That's a fake thing. It's kind of a misconception that we've all grown up with, that you impart a force into an object and that's what causes it to move. The continuous force on an object is what causes it to accelerate. But again, we'll talk a little bit more about that in class. For now, just understand velocity is not a force. Velocity, and more specifically acceleration, is caused by a net external force. So now that we've got a picture, we're going to go ahead and draw a free body diagram. And we need to think about all of the forces that are acting on this box. So here's our center of mass. Typically, you want to always draw your forces coming from the center of mass. So the first thing that I always do with these problems, since we're mostly going to be unearthing these physics problems, just like you walk into a room, you turn on the lights. Anytime you walk into a physics problem, you're going to want to turn on the gravity. So right off the bat, you're going to draw an arrow going straight down towards the center of Earth. You're going to label that FG or W. Remember, force of gravity is Fg, W is weight. They mean the same thing in physics. Now that we've got that out of the way, we've covered our field forces because there's no electricity going on in this problem. So every other force acting on this box has to be a contact force. So let's look at the picture over here and let's see what forces are acting on the box, or what is in contact with the box. First of all, we know that Phred, with a pH, is pushing on the box in the rightward direction. And we mentioned earlier, any force caused by an animate object, in other words, Phred, who is a living person, is going to be called a applied force. Now, what else do we have? There's a surface underneath the box, right? So the surface is actually pushing up on the box. Otherwise, it would just keep falling down through the ground, right? I know it seems a little weird where is the floor really pushing up on the box, but there has to be some sort of force keeping that box from falling down, because if there was no upward force right here, which we'll label as the normal force, then this object would be in free fall, right? Because gravity would just be pulling it down with no restrictions. The last force that we're going to have is up here, we say considerable friction. That means that there is enough friction to inhibit the motion, or attempt to inhibit the motion of this box. So this is our complete free body diagram. We have the force applied from Phred pushing it to the right, force of friction pushing it to the left, the normal force keeping it from falling to the center of the earth, force of gravity, or the weight, pulling it downward towards the center of the earth. Now notice, I had the forces go from the center of mass outward in the direction that the force would cause the object to move. A lot of times early on, especially, I'll see students who draw something like this, where Phred has the force applied over here, the applied force. That's inaccurate. You don't want to have the forces pushing in like this. You always want to go with this route, where the forces start from the center of mass and they go outward. Because remember, we're looking at the perspective of the box, and the box is experiencing the forces, causing it to move in the right, left, up, or down direction, depending on the balance of the forces. All right, so let's go ahead and try with example number 2. I want you to pause this video, take a minute or two, as much time as you need really, and try and make this free body diagram on your own. Don't forget to draw a picture, and get in the habit of writing all of the forces in sentences on the side of your free body diagram so that you make sure you're covering anything. You don't want to just do the arrows. I know it's a bit hypocritical because I did not write the forces last time. Just didn't have enough space with my drawing of Phred. But get in the habit of using as much space as possible, writing out all the forces that you have, and then labeling them on the free body diagram. So we have an object with a weight, which remember is Fg, or the force due to gravity exerted on the object, of 10 newtons, hanging from the ceiling by a string. Let's go ahead and draw our picture. Got the ceiling right here, string right here. Let's make this object a disco ball, actually, so it's nice. And this kind of looks like a sun, but I'm not very good at drawing, so we'll pretend this is a disco ball. It's got some, we won't even make it rotate either. It'll just be a shiny, flashy disco ball. So let's go ahead and draw our free body diagram. I'm going to make this a box just again to keep it with to keep it continuous. If you want to do a dot, that's totally fine. Our center of mass. Let's go ahead and look at the forces. We have a force of tension that is attempting to pull the box, or sorry, the disco ball upwards. We also have the force of gravity attempting to pull the disco ball downwards. No other forces actually. So this is a good example of another object that is in equilibrium. There is no net acceleration, it's just at rest. So actually, I guess we can go a little bit farther into this. I did write that it is 10 newtons. So the force of gravity is 10 newtons. We know this object is not accelerating. And again, this is a little bit of a preview to Newton's second law. If the force of gravity in the downward direction is 10 newtons, in order to keep these forces balanced, the tension has to be a force of 10 newtons as well. So 10 minus 10 gives you a total of 0 newtons, which is going to be what's called your net force. We'll get into that with Newton's second law, but it's just a nice little preview to get you thinking. All right, example number 3 is going to be a little bit more tricky. We've got two objects in this situation. We've got a 10 Newton box, which again, 10 newtons refers to the force of gravity exerted on the box, or the weight of the box, sitting on a 20 Newton shelf attached to the ceiling via 2 strings at the end of the shelf. So anytime you see 2 strings, you're typically going to have a force of tension involved. So we know we're going to be dealing with at least the force of gravity of 2 objects and the force of tension of both of these 2 strings. So it's easy to assume that we're going to have at least 4 forces in this problem. Now, with 2 objects in the same system, you're going to want to do 2 separate free body diagrams. So first, let's just go ahead and draw our picture. We've got our shelf hanging from the ceiling like so, by 2 strings. We've got a box It has a weight of 10 newtons on it. Let's put the weight of the shelf is 20 newtons. And it is at rest because obviously shelves are not just going to be bouncing up and down or accelerating up or accelerating down or left or right or anything. So this is in equilibrium, which is always a good thing to know. So what you want to do first is go ahead and draw two separate dots this time. I'm just going to do dots for the sake of space. This will be our box. This will be our shelf. Now you can analyze them separately. So the box, it has a couple of forces on it. It's obviously got, we're going to turn on our gravity switch. So it's got a force of gravity is equal to 10 newtons. And it's not accelerating up or down. It's not moving at all. So it has to have a balanced force in the upward direction. That force is going to be the normal force, which must also be 10 newtons. That's pretty much all we got for that object. It's just in contact with the shelf. So the shelf is exerting the normal force on it. It's obviously in the Earth's gravitational field, so gravity is going to be pulling it down, and we're all set to go. So next we have the shelf. Actually, you know what? I'm going to go ahead and make this a box because, well, you'll see why in just a second. So we've definitely got the weight of the shelf, which is going to be our FG. I'll put FGS here. This will be FGB. It's the weight of the box and the weight of the shelf right there. We also have, if you think about it, this box right here is pushing down on the shelf. So another force would be the force of gravity due to the box on the shelf. Now, we know this shelf is not just collapsing downward to the ground, so there's got to be a couple of balanced forces keeping it in its equilibrium state. That's where the strings come in. So we got one string here, one string here. We've got one force of tension. We'll call that FT1. We've got another force of tension, call that FT2. And eventually you should be able to realize that if this is 10 newtons down right here due to the box, and this is 20 newtons down due to the force of gravity of the shelf, these two forces of tension right here, FT1 plus FT2, must equal out to 30 newtons to keep the object balanced. All right, that should just about do it for today. I just want to leave you with a couple of helpful tips and tricks from previous AP students. Call my AP Physics 1 veterans. First and foremost, force of motion doesn't exist. That's not a real thing. What I mean by that is if we've got a box right here that's on the ground, it's sliding to a stop, but it's moving in the rightward direction, we would draw the free body diagram like this. It has the normal force, force of gravity. We know those right off the bat because it's not accelerating up or down. It's moving along a flat horizontal plane, and it has the force of friction. A lot of times in this situation, students will attempt to break rule number 3, which is don't feel like you need to make up forces to fill the free body diagram, and they will want to draw some sort of force in the rightward direction because it's moving in the rightward direction. That is incorrect. There is no force on this object, even though it is moving to the right. There's no rightward force. All of the acceleration on this object is moving to the left due to the force of friction. So it has a negative acceleration. Be very, very careful of that. The last rule as well, number 2, I guess it's not the last, but it's the last one I'm talking about. Focus only on what is happening at the instant that the object is being observed. So don't worry about what happened before this box. How it got moving does not matter. What happens after it comes to a stop does not matter. You're looking at what's happening in this situation right now. There could be a brick wall right here that this box is about to run into. It does not matter. We're looking at the instant before it hits the brick wall. Unless the problem says it comes to a stop due to a force exerted by the brick wall, just look at the friction. I guess there's really not friction because it's not touching the ground. Now it's touching the ground. Just look at the situation as it is stated clearly in the problem. All right, that's about it. Make sure you go ahead and smash that like button. Comment down below if you'd like to have a different color background in the future, if you want to add any features to these videos. And as always, don't forget to subscribe.